here. Is there a place I can plug in? Let's just to be safe, since I worked off a battery this morning. There it is. Okay. Okay. Say again? Yes, that's Twitter. That's actually my Instagram handle too, if I remember correctly. Somehow I got it. I was able to get it before anybody created. I didn't have to use numbers or anything, so it's nice and.
Okay, we're going to get started with this week's seminar. Thanks everyone for coming. I actually had a chance to. I went to the University of Michigan with this guy, so it was really good to have him up here in North Carolina. Known Dr. Batchik for probably over 20 years now, yeah. So definitely very happy to have you here. And thank you. So Dr. Batchik is the Florida Power and Light Professor at University of Florida and Director of the Nuclear Engineering Program in the University of Florida's Material Science Department. He has his PhD in nuclear engineering from the University of Michigan, which he received in 2004. Since graduation, aside from his time over at University of Florida, he was also a research scientist with the National Security Directorate at PNNL from 2010 to 2012, and was also at one point had the gracious task of being the interim chair for the Material Science and Engineering Department at the University of Florida, as our other two previous chairs will attest to. He took one for the team. He's co-developer of the Nuclear Security Summer School at Pacific Northwest Laboratory, and a member of many professional societies, ANS, IEEE, SPME, and AAP. I will leave it up to Professor Batchik to give this title of his talk and say himself, okay. But with that, please look.
Thank you, Steve, for the kind introduction. I was worried that he might mention some of the various nefarious activities that we may have.
Mohammed said I wasn't allowed to do PowerPoint slides.
Oh, okay. So it's certainly, I'm honored to be here today to give you a kind of talk about one of my research projects that's kind of been receiving more and more accolades, and by accolades I mean research funding for using a particular radiography technique called backscatter radiography to do non-destructive examination. But as program director, I'm obligated to kind of give you at least a little bit of a brief overview of our nuclear engineering program, but then I'll go into what do I mean by backscatter radiography, or what we like to call it radiography by selective detection. And we'll talk about some of the underlying principles, and then I'm going to go into, and we're going to do a lot of pictures today and show you some of the fun applications where we've tried to apply this. And I'll spend probably most of my time talking about railroad cross-tie detection and probably spray-on foam insulation. We probably got some notoriety of spray-on foam insulation. I'll tell you why in a few minutes. And then one of our big projects that recently ended, but now we're starting to fire it up again because the company is now interested in us looking at other opportunities within railroad infrastructure on how to use non-destructive techniques to try to examine things. Speeds that do not interrupt operation that you do have to be worried about. But first, let's talk about the program that we have at the University of Florida. So, Disneyland, Busch Gardens, this other city, the beaches, and Gainesville's right up here. So we're actually pretty well centrally located between Jacksonville, Tampa, and Orlando. So it's all a pretty easy drive to get to some of the major cities, even though we are, very much what I would call a quintessential college town. It's pretty much our business in the city, and that's what we do. So we're very centrally located in northern Florida, which means frost line is generally about right here. So warm, at least according to southern Floriders, freezing according to Southern Floridians. I'm from Michigan originally, where you measure how much snow you have by how high it is on the telephone pole. So I find it hilarious when people are wearing parkas and it's 50 degrees outside. So, so our program's a fairly small program. We have around 80 to 90 undergraduate students, depending on what day you count, and roughly 35 to 40 graduate students. Just to kind of give you an idea, when I returned in 2012 to UF, there were 7 graduate students. So I made a significant push, particularly as my time as director, to really focus on graduate recruiting and graduate retention to make sure that, and I think I've done an okay job since then. We currently have 8 faculty, and we have 2 open lines, so it will soon be 10. We actually just hired somebody that will start in June. I'm really excited about that because we'll be starting up sort of a new research program area in radiochemistry, and it's something that's been pet peeve, pet project, depending on your point of view, since I returned, of trying to find somebody willing to kind of start up that program. But considering that we have both colleges of medicine and colleges of veterinary medicine, there's a very large need for radiochemistry at UF. Over the past few years, we've done pretty good at bringing in funding, about $12 million or so, with nuclear engineering faculty as the primary leads from a variety of organizations. And we're beginning to see new developments in getting national awards. In the last few years, we've gotten 2 Research and Development Magazine awards. They're called R&D 100s for faculty, or those of you who have been at national laboratories. You know, this is something that the Department of Energy and the national laboratories really push a lot for. And we've been fortunate to win 2, the only 2 at the University of Florida, and they both came out of our program. One of them is what we'll be talking about today. So our areas of research, our core strengths are pretty much the top 2. Nuclear materials, given that we are in material science and engineering. So we have a lot of faculty that perform research on there, and both sides of the program, both sides of the department, both material science engineering. You'll have material science faculty that kind of focus on the nuclear side, and then we also have nuclear faculty that focus on the nuclear material side. And then we have radiation detection and measurement, and then we got areas, and then, as I said, we got folks coming in to do radiochemistry, so I'm really excited about that. We got plenty of resources and things, and laboratories and facilities. So we do have our own reactor. In 3 weeks, we'll be celebrating the 60th anniversary of the start of operations of the University of Florida training reactor, which is a 100 kilowatt Argonaut reactor. We also have a high performance computing facility that a lot of my students will use. We actually took the time to go through all the process to get MCNP legally put onto the high performance computing cluster, so I can use the computing power available. We have plenty of materials laboratories. My laboratory is actually called the Advanced Radiation Detection and Imaging Systems Laboratory, also known as TARDIS. So for those of you who are Doctor Who fans, you're welcome. And that really comprises three specific components. One is my students that work on advanced radiation detection, so that's like new materials and techniques, backscatter radiography, and we also have a deuterium irradiation laboratory that we can use for a variety of material studies, as well as look at fast neutron imaging and other potential applications of these types of sources to various things. So our DD neutron generator is something that we built with Adelphi, and that's actually one of the other recipients of the R&D 100 award, is some of the innovations. I currently have, this actually is missing one of my students. I actually have 10 graduate students. Most of them are PhDs at various stages. And you can see all the research that I do. So what do my students do? A lot of different things. And that's because in radiation detection, you need to have a lot of different skill sets. Everything from looking at fundamental radiation detector materials development to modeling and simulations, to electronics design, to do signal readout, develop software, potentially algorithms around that to extract data. But then even on the systems development side, do things like mechanical design and potentially doing things around and outside of the laboratory. So then that way, if you have challenges associated with reality, I want you to experience those, because working in a laboratory is one thing. Taking out a system and trying to go, well, how do I operate this when it's 112 degrees out, and maybe down, say, near railroad track, it's actually closer to 150 degrees due to reflection off of the rails. How do I deal with the challenges associated with trying to do measurements in environment control? So let's talk about one of my major research programs, which is backscatter radiography, and using it for non-destructive examination on things. So it's something that's completely different. So now time for something completely different. So for anybody who might recognize that, I see John's laughing. This is, of course, Monty Python. All right. So this has been supported for a very long time by a number of organizations, both from private industry, defense, NASA, University of Florida. And this research goes back even before I was even a college student. Really the earliest foundation, in fact, in 2008. But he started this in 1998 when detector technology really wasn't quite there, but then has continued on since. I basically started helping out with it as soon as I got there, because I felt in 2004, because I felt as though it was a really interesting project that I thought I could contribute to. But basically what we're trying to do is just take advantage of the fact that you have Compton scattering from various X-rays, and depending on material you get different amounts, and then depending on energies and materials, different amount will scatter back towards the original source location. So that's what I really want to take advantage of. No, understanding that above things like above 1 MeV or so, this kind of becomes impractical as a technique, because all I'll be doing is playing dose to an object without getting enough signal back towards my detectors. But in a number of applications, if you think about radiography, I like transmission radiography, like you'd get at the dentist or you get at the hospital, sometimes at other facilities. You have an X-ray generator, and then and you have some object, and then on the opposite side you have your detector or imaging receptor. So in backscatter radiography, sometimes you don't have access to the opposite side of a material. So what do? So in that case, you can, let's place the detector on the same side as the generator and just see what Compton scatters back towards the detector. So if I do that, just like so, yay, I get scatters in this particular direction back towards the detector. Most of the signal will actually come from near the surface of the material, near the object. There will be other stuff that'll happen deeper that'll actually just contribute to sort of noise. But really, what might be interesting is what is the signal, what is this signal, and can I extract this signal out appropriately? Our technique kind of develops where we take a highly collimated beam of X-rays and photons and basically collimate that down, get a nice pencil beam or fan beam or some other beam geometry, but really those are the only two. It scatters off an object, and even if it scatters multiple times, as long as the first point of where it scatters is maybe some subsurface feature, I have a detector, but I collimate any sort of near surface scatter from interacting with my detector. So I basically shield it out, kind of like, if you think about line of sight, I basically have prevented me from having any sort of line of sight with the top surface of the detector, and then anything that comes down from beneath, I can actually measure that, and if I can raster scan over an object or scan over an object via some other method, I can easily generate an image. So give you an example of why this can be important. So here I have sort of just a simple Monte Carlo simulation where I have basically foam layers and an aluminum substrate, and we'll show you where this can be. This was a particularly important example, and I have a detector and I have a collimator with just a simple pencil beam. And realistically, what I really want to see is what is this aluminum substrate. So if I have a flush collimator, which means I didn't have any collimator on it, you get sort of signals from all these layers of material. But if I add that collimator, I can, depending on the length of that collimator, I can sufficiently suppress the signal from, say, top layers of material and actually enhance the signal coming back from both the substrate, which is now the majority of the signal, but I still get some from multiple layers. So what can I do to maybe eliminate these multiple layers is potentially use multiple collimated detectors, each that are specifically collimated to specific depths within a material. So I really should update this because we're talking about a technique that's been developed over 30 years now. So it's not really a new type of Compton backscatter imaging, but not a lot of people utilize it. So I'll still call it new for the time. And I can look at different types of scatter components from different layers, which allows me to potentially create multiple sets of images from a single scan. So now you can start thinking about things like, oh, can I create 3D images? Can I create objects that are maybe can be easily detected? And really what I'm doing is trying to create signals that allow me to create images and produce images with easily recognizable internal structure or defect details that allow me to say, is there a flaw or is there something else there? So what you try to do in this is it's a lot of optimization. So you try to optimize for a variety of different things. If you have particular detectors you want to use, or more importantly, if you're going to use different types of beam geometries, that's going to put constraints on your detectors. So I'm going to guide you through this a little bit to see how you do. But what we like to use as much as possible is commercial off-the-shelf systems or components. So then that way, when we do design these systems, often there's sort of an industrial application in mind. It would be good for end users if they don't have to rely on a universal individual components. So we try to use just standard sodium iodide detectors. This is yttrium oxysilicate, I think that's YSO, that we tested at one point in time to look at different signal strengths for different detector materials. In our system, we have 4 different this is one geometry that we use, 4 different detectors, each with its own individual collimation, and then a collimated pencil beam that extends out here. If you see this yellow, that's actually the X-ray tube itself. So you have it all housing. These detectors are all housed around the X-ray source. You might ask, do you have to worry about interference from the leakage from the tube itself? The answer is absolutely. That's why you design housings to shield out any sort of leakage radiation from the detectors, and then you do kind of some light and dark field images to basically calibrate the system so that way any noise gets somewhat subtracted out. So our first application for this was actually in a defense application for landmine detection. So landmines have prescribed geometries and are buried to specific depths, whether it's anti-personnel or anti-tank mines. So anti-personnel mines are pretty difficult for non-destructive testing, non-destructive imaging techniques like terahertz imaging to detect. They're a little bit closer to the surface, and at the same time, the geometry is much smaller, which makes it difficult to prove that it's a lot of false positives in some of these techniques. But we were able to actually have a testing event at Fort AP Hill, which allowed us to basically raster scan over an area and actually generate pretty good images. So you have a couple collimated detectors, and then we use an uncollimated detector because, as I mentioned before, your uncollimated detectors will get a lot of surface scatter. So we're actually able to subtract out what might be on the surface from what might be, from our actual images. So what you actually see here is landmine and a landmine, and notice front and back, and there's some slight offset that you have to basically correct for because of the difference in position relative to the beam, but that's easy. That's just an alignment. That's just an alignment correction that you do for each of the images. But you can see here that each of these images actually have this little blip, which is actually a rock that was just slightly buried underneath the ground. So we are actually able to subtract that out and render a final image that is really just based on the void that's underneath the pressure plate of the landmine. So we're able to scan an area about 10 square meters in 40 minutes. So timing was basically what killed this experiment for real field application, because no military person is going to want to, no Army personnel are going to want to scan over 10 square meters in an hour. It's just going to take too long relative to other potential techniques, even though we're the only technique that at the time when this test was done, which I believe was 2005, was the only one that could detect the anti-personnel landmines. Anti-tank, a lot of different techniques could easily see that. But in applications where maybe you don't have to worry about time, so more like laboratory settings might be a particular fun and particular interesting place to put it. So if we go back to your younger days, all the way back to 2002, you had the Columbia shuttle disaster, where a piece of shuttle foam insulation broke off the external tank, struck the wing of the Columbia, and basically broke part of the heat shield. And they knew pieces of debris falling off during launch was a particular problem since the first launch of the space shuttle program back in the 70s. So as a result, you had the breakup. But then they're like, well, what do we do for our space missions that we need to accommodate? So one of the things was to look at what non-destructive examination techniques might be able to accommodate for that. So what the particular problem with this is how this is applied. So most places on the external tank, this can get applied robotically. But there are certain places where it was always applied manually. See this on the screen? When it's applied, you apply a layer, then it expands a little bit, and then you apply another layer, and you want all those layers to kind of knit together nicely. But if you don't time it properly, these knit lines don't kind of come together quite right. So you end up with delaminations and voids that can easily occur in this shuttle foam. And like I said, it's particularly a problem around certain areas where it had to be applied manually. And that included some of the areas where the shuttle sort of attaches to the external tank, as well as where some of the booster rockets also attach to the external tank. Actually, that's along here, along the boat flange area. So came off, and NASA was looking at this because they saw the report on some of our techniques as we were building the landmine detection, and thought, well, this might be a really good application for looking at this. So they asked us to build them a prototype system, which you can see here, which again comprised of just the sodium iodide detectors and a lead line pencil beam geometry that would just raster scan over the material. And this is kind of one of the test pieces that they gave us that had some known flaws and for an object debris in the material. Let's see here if I can get this to, there we go. So we scanned over this, and you can kind of see some of the parameters for how we would operate. This is usually like a At the time, we were using a 60 kVp tube for spray-on foam insulation at 0.03 grams per cc. It's pretty, you don't need to have a very large and heavy X-ray source to do this. But we basically had roughly 2 feet by 2 feet area, and you can kind of see the rendered scan right here. You can see in this case we were using all four detectors to basically give you a single 2D image and see some of the change in intensity as a function of thickness of the material. But some of the things that you can easily see are certain structures like the tank flange. You can also see some of these glue lines or knit lines that actually occurred on some of these materials. So you can actually potentially evaluate those. You can kind of see a stiffener stringer. It's located right here, right here, and right here. So you can actually see a lot of the structure. In addition, you can see all sorts of fun foreign object debris. So let's go and take a look. So obviously we got sort of a mechanical pencil that they embedded. They put some tape, some bolts, and you might sit there and laugh, but when you get and you work in an operational field where you have technicians and you got people that are scrambling to get this work done, this stuff will appear in all sorts of things. So one of the systems that we built and tested for Boeing can actually go down fuselage and actually scan and record images, and you'd be surprised at what's left in between the panels. I probably shouldn't have said that since they're having so many issues with the 737 MAX 8, but that's actually a particular concern is foreign object debris in different materials, and this is no different. So you got debris, but one of the things we were also able to pick up, you might not be able to see some of them, is actual natural defects that actually occurred due to the voids and delams that actually occurred in the application process. So a lot of our a lot of things that we look at is this, and then also what types of geometries give you the best count rate, but also best contrast, because in imaging you want contrast, so that way you can identify features and flaws with a higher degree of precision. So you look at things like count rate versus current mode. Generally, we are operating with high current, so you want to operate with current mode. You get less you don't have to worry about pulse pileup, like reducing your actual count rate. You're just looking at current mode, so you generally get slightly better contrast for different things. This actually happens to be a heat shield tile, carbon-carbon composite tile with some voids. There's actually 4 here. You can't see the 4th one with different sizes. But this actually gave us opportunities to look at other objects. So this happens to be, a piece of aluminum aircraft component. And what you're normally seeing here, because it's not fun to look at the unflawed version, because you just go, well, it just looks like a normal painted piece or something that's covered up. So we include if you remove the 2 millimeter skin overlay that's also included on this, you can kind of see some micro cracks, and you can actually detect that. So even if you have a beam that is larger than the flaw that you might be trying to find, you can still generate an image that will give you the ability to detect, maybe not necessarily image as well, but be able to detect flaws and features of interest. Here's an application for our reactor pressure vessel steel, where we just slabbed on some boric acid. We added the label so that way we knew where we were position-wise. So that's why you kind of see that right here. But you can easily see that deposition from the opposite side of the reactor pressure vessel steel. So you're going through this and coming back through this insulation, and you can actually see that boric acid. So you can kind of see where potential commercial applications of this might be within the nuclear industry. Homeland security applications with peering at things behind the walls. This is actually an important part. And Dan Shedlock, who used to work for Varian, did a lot of this work on generating these images, where now you can kind of see, could we see listening devices behind walls, for example, and this is actually a good application of that. But I want to talk to you about, spend a lot of time talking about this project, which was a lot of fun and very interesting because not only laboratory, but this is actually a project that went all the way through commercialization that students in my group got to enjoy, which is looking at trying to image railroad crossties and evaluate their condition and try to do this at reasonable speeds using backscatter radiography. So if you look at, this is a project that was sponsored by Georgetown Rail Equipment Company, who have been partners with me for a while now. If you look at how you do railroad crosstie inspection, there's visual inspection, which is what most places have been doing up and still do today, which is somebody walking the track and kicking or hitting the crossties with a hammer and then going, it's a 4, it's a 3, it's a 2 in terms of grade. So very subjective, right? Very fraught to individual errors and judgments. So there's the company Georgetown Rail kind of built sort of a surface scanning system using 3D LiDAR capabilities to be able to go down and at least map the elevation of that. And that can be one factor in tie grading. But what are both of these things missing? That capability of how do you really truly try to assess that below surface structure. So, the objective of this was to develop a prototype system that can successfully image railroad crossties, both wood and concrete. In the United States, 80% of the crossties, which if you actually calculate the amount of Class 1 railroad in the United States, and then you multiply that by 2,200 crossties per mile, roughly, it gets to be a very large, hundreds of millions of crossties that need to be inspected by Federal Railroad Administration regulations every 7 years. So there is at minimum. So, and then as they grade, inspection actually goes up. So there is a significant importance to actually generating an inspection system that can inspect at realistic speeds. So challenges for this included, how do you use a large X-ray source on live railroad track and allow it to scan and go pretty much across the country, across state lines, and not potentially irradiate people. You have a large scan area, and if I got to do this at reasonable speeds, I got to get away from raster scanning with pencil beams, which is awesome for laboratory use, and move to fan beam geometries as well as linear detector arrays, so that way I can collect this data reasonably quickly, and then potentially have to sync this data with other inspection technologies, and then keep in mind that control may be fleeting. So how do I ensure that this system can be worked on in Arizona in August or North Dakota in January? Those are a lot of the challenges. So what we do is we take an X-ray tube. It actually has a fairly far standoff distance, which we can take advantage of to fully irradiate the cross tie. But at the same time, flux gets lower. But the other thing that I'm doing is avoiding an additional Federal Railroad Administration limitation, which you have to have a minimum set amount of clearance on the railroad, so that way you avoid debris and trees from impacting measurement. You don't want to start knocking stuff out that might hit and cut a fuel line or something like that. So there's it's called Plate C, and basically says that I have to have roughly 18 inches of clearance between cross tie and any sort of bottom surface. So, and then we have a linear detector array that we collimate. So we have a linear detector array that gives us one dimension, and then we're moving this in this way. So if I can have something that will take data at a very high speed, and I encode that with use a position encoder, I can actually generate both sets of position information, X and Y. So even though I might be able to get finer position resolution with something that'll raster scan, and maybe my detector requirements aren't nearly as significant. I can actually increase speed, even though I might have to accept that I'll get worse energy resolution. Instead of millimeter scale, I might have to look at several millimeters to maybe even a centimeter. But in the railroad industry, that's what we kind of found is that if you try to have too fine of resolution, some of the algorithms for decision making become confused, because they'll think the fibrous nature of wood becomes a flaw, when that's not really the case. What we're looking for are more the gross flaws that lead to weakening systems. One of the other advantages of going to the fan beam source is when you actually have a larger standoff distance relative to position, because on raster scanning systems we can have something that scans really close to the surface, but in this case, because of the Federal Plate C regulations, as well as what we wanted to do in terms of radiation area, we actually, fortunately, have the advantage that a larger relative amount of the beam strength actually comes back towards the linear detector array. So that actually lends itself to a better, faster image acquisition after all. So we did all the modeling around to look at these materials. This is actually a different material, but it's same basic platform where we look at, how do we collimate the detectors to basically optimize the collimation relative to a particular position. So then that way we can get a decent image without being under-collimated or over-collimated. And you got to be careful about this, because if you look, I go from, my basic, in this case, this void appears dark, right? When I'm in decent collimation, under-collimation starts to lighten up, but when you start getting over-collimated, which means I'm starting to, I might try to see deeper into a material, that image and the image intensity kind of flips. And that's actually a particular challenge that you got to work out. Now, in our case, we were able to take advantage of the fact that we know that degradation occurs primarily one of two ways. Usually from the bottom up, so that's due to like water intrusion, or from the inside out, and that's wood-borne organisms that might get through because they didn't properly treat the outer surface of the cross ties. So working with a company called XScan Imaging Corporation, which is based out of San Diego, California, we actually developed a prototype detector, linear detector array, and they were working on high-speed electronics for security inspection systems. So most of 90% of their, I'd say 99% of their business is like cargo inspection systems for airports and things like that. But they custom built a system that can actually operate and collect data at 9,000 lines per second. So pretty high-speed camera, X-ray camera essentially. They actually have a system that can now do 18,000 lines per second. But in our case, we operate usually in the 2,000 to 4,000 range. But one of the advantages of this is this allowed me to work and collect data if we travel even up to 50 miles per hour on track. And the nice part is that the vehicles are limited to 25 miles per hour. So this means one of my goals was to not let the inspection system become one of the limitations for use on track. In our case, we designed with their standard geometry actually worked reasonably well for 1.6 by 2.4 millimeter resolution. There are other dimensions that they can build for you, but obviously that comes at that customization cost. So, in addition, we add an additional collimator, which we'll talk about in just a minute. The detector material itself is actually just like a gadolinium oxyorthosilicate, or cesium iodide or sodium iodide material that just sits in sort of this channel. So you already get some natural collimation to begin with. in addition to then being fiber optically coupled to a CMOS active pixel array. So CMOS gives you the high-speed readout, but the cost to that is CMOS tends to degrade faster in at less radiation environments. So you have to house this detector in a fairly large tungsten shield to basically ensure that your CMOS does not get suffer too much radiation damage over the period. And then one of the big challenges for us is the shielding doesn't need to be on the front end like you normally do for traditional transmission X-ray detectors. It actually needs to be on the back side in order to accommodate for the fact that you have to shield out any sort of leakage radiation from the tube itself. So the reason why we need to add additional collimation is if you just record the signal as you scan down a system in one dimension, each of your individual detectors is getting scatter from basically that entire line, and you don't want that because then all you'll see is basically a blur of the lines that you might scan over all convolved together on each individual pixel. You can try to deconvolve that. It does not work. But if you add the collimator, you basically shield out sort of, and then that way the detector is really only looking at a fine volume of materials. So now all of a sudden I still get my X direction, now I get my Y direction pretty easily, and then I can render an image that's fairly useful. So whenever we do prototyping, as my students will attest, any of my students that have worked on this get to build a collimator out of lead fins, which means they get the of cutting lead, which is time consuming and everybody hates it, but it's like, it's easier to do than for prototyping purposes, because once we know the exact dimensions that we need to work with, we can build the tungsten array that kind of accommodates for strength, and then you don't have to worry about that. But this is what you see when you actually get the image. So on the right, you can kind of see sort of a new tie, and then we laid down some wood that we put Georgetown Rail Equipment Company, they shorted as GREX. And you can kind of see UF here, and we can actually image looks better on the computer, but that's okay. You can see what you get for a good tie as you're scanning. This is just a single motion. So you see a little bit of degradation in the signal on one side of the tie versus the other. This is partially due to line of sight issues, because we only, for the prototype, we only had a single detector, so one side gets a little bit more shielded on one side than the other, and then you kind of see some of the lead some of the lead kind of occluding the signal. You can kind of see that overall. This is just a thin piece of wood, so that's why you don't see it nearly as large return signal as the good cross tie, which is basically 9 inches thick. So 22 centimeters. Now you go over degraded cross ties, and one of the things that we did as part of the project is we have our own railroad track at the University of Florida. It's part of my lab. It's called the Boric Railroad. It's about 100 feet long. I'm really proud of it because I have my own railroad. Say again?
Does it run on time?
No, never. Absolutely not. So you can see here that you kind of get shaded areas that ultimately are reducing in sort of grayscale value, which is basically shows that it's basically an elimination of rho T, or mass thickness of the material. So you actually can see places where you no longer see that uniformity. You can have surface cracks that might reduce the signal a little bit, but as long as it's just a surface crack, something that doesn't extend down deeper into the material, you don't see too poorly of a degradation. But it's very easy to end up with being able to show that these are so bad, so you can mark them as good, or you can mark them as a fail. And so then that way, railroad operators like CSX or BNSF, where they have to maintain these freight lines, and freight by rail is still one of the most economically methods of transportation of materials across the country. So maintaining these rails, because once you start losing several of these cross ties start to fail in a row, that's when you begin to lose railroad integrity, and that's one of the potential mechanisms for derailments. So, so one of the things that we wanted to do, and one of my students, who's now an professor up at Brown University, looked at ways in which we can adapt how the medical industry actually goes and does imaging spatial resolution. And that's by basically doing Fourier transforms and investigating the modulation transfer function, which basically provides a complete description of system spatial resolution as a function of the spatial frequency. And the reason why it's nice to look at that is normally in terms of medical QA, you look at where the MTF value crosses 10%. And the reason why 10% is that's the average human's eye for resolving two objects or two lines together. So there's different ways in which you can measure this in terms of transmission. So you can use what's called slit methods, or you can use bar patterns or slanted edge. We looked at bar patterns and slanted edge that give you square. This is sort of a square wave analysis technique, or this is called a knife, sometimes called knife edge. The reason why you want to slant this is so then that way you don't create sort of a bias because of your pixelization on the individual detectors. If you line everything up properly, you can kind of artificially improve your resolution. So by slanting it slightly, you ensure that you go over numerous different pixels. So again, this is a commonly method used in medical imaging. So we wanted to we adapted it for all. And we actually investigated, and it actually turned out and worked pretty well. So here you're looking at two different scans. When you see a cross scan, that is across the cross tie, or no, that's across several cross ties, and then a long scan is in the direction that's basically parallel on the linear detector array. And you can kind of see in both dimensions, for the most part, you get the same MTF curves. So you can follow down to 0.1 and basically go, okay, it's roughly 0.22. We've scanned these over several times. Basically, our resolution translates to about 8 to 12 millimeters in real position values, not necessarily in frequency space, but that kind of gives you an idea of how closely we can separate out flaws and features of interest, which is sufficient, easily sufficient for the railroads. There is a little bit of difference between in this edge, a long scan technique. Part of that is also, differences in how we sample, in part because we have 2.4 millimeter resolution pixels or pixel pitch in one dimension, while it's 1.6 millimeters in the opposite direction. So that kind of gives you a little bit of an idea of why we get some discrepancy in one direction versus the other. But we were able to go from essentially a laboratory system that's kind of scans and does fun things in the lab to students working on all of the MCNP simulations, including all of the work that went into getting this approved with the various state regulating agencies to ensure that this system can go on live track and then go across state lines. So we actually worked with the state of Texas, which actually has some of the most, for as Wild West as people think the state of Texas can be, one of the biggest restrictions they have is in industrial radiation sources, because that's where a lot of the oil well logging industry is based out of. So they have some of the toughest regulations when it comes to industrial radiography for those reasons. So working with this company that's out of Georgetown, Texas, actually worked out well in that we were able to engage pretty much some of the strictest regulators that even enabled us to get this system approved for use in California. We built the prototype system, so I will say, please do not mind the slight bowing in the middle of this prototype trailer hitch system that could be attached to a high rail vehicle. We were not mechanical engineers, so one student may have forgotten to add the weight of the lead shielding that goes on the inside of the and around the X-ray source, which is about, when you're talking about, something that is about 12-inch diameter X-ray tube, and then you got an additional inch diameter of lead shielding. That is not an insignificant amount of weight. Well, we were able to shore that up and get it to work right. So we were able to test this in front of chief inspectors for BNSF. And how do you confirm non-destructive testing? Through destructive testing. So this cross tie itself was actually graded as a good tie by the chief inspector. Our conclusion was we believe it is completely hollowed out. So I got the joy of using a chainsaw to cut this open. I destroyed my chainsaw, by the way, but that's okay. Because we were able to show that actually this cross tie was completely degrading from the inside out. So, my sponsors were there as well. They were really excited when we showed this in front of the chief inspector, because we didn't know that this was we were like, I hope this works. And sure enough, it worked out well. So they ended up buying and commercializing the system. And my students got to work on all the shielding aspects for this. They got to work on some of the mechanical engineering aspects of this, getting how do you power this system. We tried powering it off of the engine itself, but that wasn't a stable enough power, so we had to use a generator on this. But it actually worked out very well. We got to do all the testing and move on and start looking at other things, like how do you do this for concrete? So I can't get through 7 inches of concrete. It's just impractical. But I can certainly get down to, say, roughly the first layer of rebar, which is some of the failure modes for this material is degradation of the rebar that ultimately starts leading to cracking. So we were able to show, at least with some target objects, that you can get debris. So this is a little bolt, and then I had a wrench that was embedded in this. We actually embedded some of the targets into some concrete to do some taping, but there's other applications where backscatter radiography could lend itself to interesting applications. So here's a pig cadaver where you have, maybe you have the hip and you got the spine that's underneath. If I want to look at the spine, I can collimate out the signal from this, so I can look at different depths within a cadaver itself. So for medical applications, you can look at things like, if we set up an array of detectors, maybe we can do single-sided CT and do this at doses that are more prevalent in traditional just radiology as opposed to CT. So you're talking about potentially orders of magnitude savings in terms of dose to patients, with the potential for normal throughput rates at hospital facilities. You could look at this, I could maybe set up something for emergency imaging, so I don't necessarily have to move a patient who might be on the ground, scan over them, and maybe do triage in the field by communicating with emergency personnel back in the ER facility, or even look at things like compressionless mammography, where I could potentially just scan over and do a mammogram instead of having to listen to Becky complain, who's my wife. But one of the other very interesting projects, and I know I'll wrap up here in the next minute or two, is to look at plant root structure by imaging roots, and then can we use that image combined with other data that we can get from plants to actually determine interesting things. For example, how much carbon sequestration might occur from particular crops and particular plants. So then we can get a measure for how much carbon might be removed from the atmosphere in the world of climate change. This is something that people want to think about. Can we better optimize water usage in by different plantings and knowing how these root structures are developed. Now, there's plenty of people that do root imaging. There's the Danforth Center for Plant Science in St. Louis, Missouri, but they do it in mesocosms and in large planters that interrupt natural root growth. So this is a way in which we may be able to scan over the surface and actually get some root features. So this is actually a combination with Alina Zaire, who's in computer engineering and does machine learning algorithms, myself, Scott Kowaleski, who's one of Steve's colleagues, who's at the University of Missouri, Columbia, and researchers from a variety of other national labs and universities and organizations. So it's a combination of looking at genetics, plant modeling, phenotyping, farm and crop facilities, image analysis, machine learning, as well as developing a backscatter system that could potentially do these types of roots. Now, I can't go, forever deep, but we're trying to push towards developing something that can go through about 8 to 12 inches worth of soil. So, I mean, it's nice when you can do the CT images, but this is not natural field applications, so these roots don't necessarily grow naturally. But one of the important things that's important here is that at least within that first foot of soil, that's where 95% of root structure lies with most crops. So it's something that can be easily potentially imaged. Here's some of our first attempts. I know this doesn't show up very well. It looks really nice on my high-res screen, but it doesn't show up very well on this screen. This is switchgrass roots, and we took some images both with dry roots and wet roots. The wet roots give us a little more contrast. That water actually helps us out, but you got to be careful with that because we got to look at soils and water composition within soils themselves, because water can both be a contrast enhancer, but if it's in the soil, it might also be a contrast inhibitor. So we got to look at what that balance is going to be. So that's one of our research research endeavors right now. So backscatter radiography does provide a method to uniquely inspect things where traditional radiography is not possible, and it works well and complementary with other imaging modalities. So we've demonstrated this in a variety of situations where our current push is to look at potential medical imaging applications as well as within plant science. So it's kind of fun because I'm sitting here talking as a nuclear engineer, and at the same time I get to learn a little bit about plant science along the way. Now my family, incidentally, I have a lot of background in farming, so that's kind of fun. Incidentally, Google is actually interested in this project for farming applications, and their particular interest is being able to go through a vineyard and identify grape clusters, through the canopy without having to disturb the canopy. And all I'm saying is free wine, maybe. But this is a complex system that has complex optimizations and compromise in terms of what you want to do with speed and image quality. You got radiation safety concerns that you have to deal with, and then how do you design for field conditions, which just requires a lot of environmental testing capabilities. So a lot of students have worked on this project over the years. Dan Shedlock was a big push early on. He's now at Varix, which is an offshoot of Varian that does sort of some of their industrial and security imaging systems. Chris Mangs now works at, I believe, within the Department of Defense. I'm not quite sure at this point. Michael Eisenfeld actually was hired by Georgetown Rail, and he kind of handles some of their current research endeavors. Jessica Salazar was a big component of this project as well. Travis is now at West Point teaching physics. And you can kind of see a number of other several other members of my group that have contributed to this. So I want to thank you, and we can spend a couple of minutes doing questions, and this should, if hopefully it works, we can, no, little, it sounds very Texas. But you can at least watch the video while we answer questions. But if you have questions about what you might see on the video, I might be able to help you out. Okay, thank you, everyone.
So, Jan, it looks like that you use different sources because I recognize that the power operational conditions
Yes.
vary between as low as 55 kV
Yep.
to as high as 450 kV.
Yep.
In the Fab 1.
Yep.
So, is the 450 kV the one that's on the vehicle, inspection vehicle?
Yes.
Was it sufficient to power the source? Because you said you have to put a generator for this.
Oh, yes. So I believe the company for the wattage on our system and at UF, I believe is 1,500 watts. But I believe the railroad system is using a higher wattage system.
Now, the other thing which is very interesting but also very challenging, which is the compression-free mammography.
Yes.
You mentioned this, and I know that we had some discussion together about it. But, you know, is there any preliminary experiments for compression-free mammography?
Is there any?
Preliminary.
No, I haven't made any preliminary result. This is something that's in my head that I haven't been able to find the right student, and then with balancing all my other responsibilities, I haven't had time to really pursue that.
It would really one of the biggest breakthroughs.
I think so. That's why I kind of keep trying to push and trying to convince some students that they want to do that. But if I have, if you look at, here in Research Triangle, you got a couple more medical-oriented universities here where reaching out and doing some collaborations that I got to explore. This might be something that may be of interest.
Yeah, I think so, yeah.
Yep.
I think according to about half the population, they should be at the top of your list.
Yes, probably.
Could you describe how the transition from the proof of concept went to getting it out as the commercial product? How that worked?
So a lot of discussions with our Office of Technology Licensing is one aspect of it. But the company, Georgetown Rail, was really supportive of it. And ultimately, what we developed in terms of the agreement was actually joint IP. So they really were interested in this work. But they want it for their application space. I'm interested in it for other applications as well. So what was peeled off was they get kind of exclusive rights for railroad inspection. But I'm able to look at using this, in part because, this is our type of system that we've designed. I can use this for other techniques as well. So company itself was actually wonderful to work with. That's why I've ended up having like 3 separate projects with them for various things. And my hope is that we continue working together for a number of years to come. It's really fascinating kind of working, for as old and mature as the railroad industry is, there's also a lot of really cool opportunities on bringing new technology into that area that will help make railroads safer, easier to use, and reduce costs for maintenance and mitigation of issues. And it's extraordinarily important because with as big and as wide as railroad is, just a small cost savings per mile translates into hundreds of millions of dollars. Same thing just like the nuclear industry, right? If you can shave off fractions of pennies of kilowatt hours from kilowatt hour generation, that translates into millions of dollars of savings over a year and over tens of millions over the life of a plant.
Just a quick follow-up on that.
Sure.
You had students working on that project as well, right?
Yes. Yeah, I had ultimately at any one point I had 3 or 4 students that were working on it.
Did they get involved in the IP?
Yes. So some of my students are actually considered the leads of the IP that was generated off of it. I'm not a big, have a huge ego. As a university researcher, I don't like patents because I feel like it inhibits my ability to publish and other stuff. But I understand their importance, and ultimately, especially when students are on these commercialized systems, there are some restrictions to publication. But the patents is actually one way to get their names out there, and so that's why I actually encourage students, if we do have commercialization pathways, that we actually explore those. And I put their names, I try to put their names first, and just like on a paper, their names go first. They're the ones doing the work. I'm just providing guidance and encouragement. They're the ones that are really doing the true breakthroughs. They should get the credit for the patents.
Since you use a CMOS, do you have any rolling shutter effects you had to deal with?
Say again?
Since you use a CMOS, did you have any rolling shutter effects you had to deal with?
Not at this point, but I know the company tests their detectors before sending them to me, and I can tell you that at least on one occasion there were some significant delays, so I think they've tested to ensure that I don't get some of that rolling shutter effect.
Also, in your image of the nylon and the foam, the nylon bolts in the foam, it seemed like it was exposed differently in parts.
So part of that is because the thickness of that material is changing, so I'm getting less signal or more signal back depending on if I'm on one side or the other. That's the primary reason for that. And that was just a 2D rendered image where I didn't try to go back and sort of make adjustments for that thickness in the material.
Any more questions from the audience? Okay, let's thank our speaker one last time. Thanks very much. See everyone next week.
Right level?
Huh?
Right level?
Perfect. Okay. Perfect. You can tell that I didn't fall asleep.